Welcome back, learners. In our previous session, so we have made everything ready in order to do the design of the beam. Now, out of this, let us take the first beam that you can go from the beam number. You have made a grouping that beam 26, 27, and 30. Right. If I look into the beam 26, 27, and 30, you can see that beam 26, okay, that is this one, 27, second one, and beam 30, so the third one. If you see this beam 26, 27, 30, the dimensions of the beams are 9 inch into 1 feet 8 inch. So therefore let us make the first group of column, that is I can give the name as 26, 27, and 30. We have previously defined that the grade of concrete that we are going to use for the beam and slab will be M20 grade of concrete, and the grade of steel that we are going to use will be 415 grade of steel. The breadth of the beam that we are going to use here is equal to 9 inch, that is nothing but it is a 230 mm width beam. Okay, and the effective cover that you are supposed to consider for the beam, as per IS 456, the minimum effective cover to be provided for the beam will be of the 20 mm. Therefore I am maintaining a 20 mm effective cover. And what about the effective depth of the beam? The effective depth of the beam, it is 1 feet 8 inch beam, that is nothing but 510 mm. Okay, so therefore the overall depth of the beam will be 530 mm. Okay, the overall depth of the beam will be 530 mm. Right? Yes. So now according to this table, right, according to this table, this is the M3 negative, that is negative bending moment, and M3 positive, that is positive bending moment, and the last one will be shear. Now before I move on to that, I would like to make you very clear that yeah, so now when I take up a beam like this, okay, when I take up a beam like this, and when this beam is resting on a support like this, okay, when the beam is resting on the support like this, now usually keep it in mind, students, the negative bending moment, okay, the negative bending moment will always be developed at the support. Okay, here at the support I can have your negative bending moment, right? So if I choose in this area, usually your negative bending moment always exists, that is at the support. Okay, so your negative bending moment always exists at the supports. Okay, so this one, it is always, usually it will be negative. Here the moment that you are going to see will be always negative. Okay, whereas if you see in the middle of this, if you see in the middle of the beam, here it is always the positive bending moment. And especially I can say that if you want to be still more accurate, I can say that your negative bending moment will be available at the support, especially at the top of the beam here, usually at the support and at the top of the beam your negative bending moment is going to present, whereas your positive bending moment is going to present at the middle of the beam and especially at the bottom of the beam. Okay, especially at the bottom of the beam. So these two things we are always supposed to keep it in mind. So therefore according to that, okay, according to that if you see, okay, according to that, so now the negative bending moment that I am going to see is 173.249, whereas the positive bending moment that I am going to see is minus 144.775. Okay, so and the shear force that you are going to have is 238.14, which is obviously it is a shear force in the kilonewton. So therefore I can give that the shear force that I am going to experience is 238. I can make it as 240. Okay, it will be 240 the shear force, which will be in the kilonewton, right? So now When I go to the design bending moment, I told you that we have two types of bending moments here, positive bending moment and the negative bending moment. Now they have asked you the positive bending moment. You can see that the positive bending moment is that I am going to have here is 173.249, that is positive bending moment. Okay, whereas the negative bending moment is this value, that is minus the 344. So the positive bending moment I can make it as 175. Okay, the positive bending moment I can make it as 175 kilonewton meter, whereas the negative bending moment I can make it as 345. Okay, I can make it as 345, and here the negative bending moment doesn't indicate that you are supposed to take negative. Since it is at the support, we are going to call it as negative bending moment, and at the bottom we are usually call it as positive bending moment. So therefore I am taking negative bending moment of 345 at the support, right? So therefore by looking into this, automatically based on mu by BD square value, we are going to get the value of this mu b by BD square, that is for the positive, whereas even this we are going to get for the negative. So once you get the value of mu by BD square for the positive bending moment and negative bending moment, so from this, by obtaining this value of PT, get the percentage of steel required. Okay, so get the percentage of steel required. So definitely the percentage of steel that you are going to get will be from this table. You know, this table is for the FCK as 20 Newton per mm square, and you know the value will be 415. Okay, the value will be 415. Okay, now by looking into that, you can say for the positive the bending moment value, okay, the percentage of steel for the positive bending moment will be 1.2. okay, that is that we are supposed to enter the value. The value of mu b by bd square is 2.9. I can take it as 3. You can see that where the value is there, that is for the 415. Okay, you can see that the value is not available. Okay, the value is not available. The reason is you cannot give that much percentage of steel. Okay, you cannot give the percentage of steel because for M20 grade of concrete it is not available. Okay, because the value of shear is very high. Okay, the value of shear is very high, so therefore you cannot go, right? So therefore what you can do is either you can increase the grade of concrete, or you can increase the dimensions of the beam. Okay, so therefore from here I will go to the value as 25. Okay, I'll go to the value as 25, and I'm going to increase my breadth of the beam as 300 mm. Okay, and even my effective depth of the beam I'm going to make it as 550. Right, so therefore now the value has become 1.9 and 3.8. okay, so therefore you can see that for FE 415 and with the 25, you can see the maximum values are available here. Okay, so you can see that mu by bd square value. So now what is the first value of mu by bd square for the positive? For the positive, the mu by bd square value, okay, it is 1.9. I can go to 1.9 here, and FE415 is here and 1.9 is here. It is 0.538%, 0.583. So therefore I can enter the value as the percentage of steel as 0.583. okay, whereas for the negative bending moment value, the mu by bd square is 3.8. okay, you can see 3.8 here. Okay, the maximum is 3.74. therefore you are supposed to provide that the maximum value is this. You cannot go, you are supposed to provide 1.189. okay, 1.189, because the value of the negative bending moment is very high, so 1.189. okay, you can see that I can give the value 1.2. okay, 1.2. So therefore now you can see that the area of reinforcement required will be 996.93, whereas for the negative it is 2052. Okay, now let us go to that, the diameter of the reinforcement that I am going to consider. Okay, for the positive will be, let us take it as 16, whereas for the negative reinforcement let us give the value as 20, right? So when I give that, you can see that the area of the individual reinforcement will be 201 for the positive, whereas for the negative will be 314. So automatically you can see that the number of reinforcement required on the positive side will be 4.9, so I can make it as 5, whereas the number of reinforcement required on the negative side will be 6.57, means let me make it as 8, and this let me make it as 6. Okay, yes, so this is how the number of reinforcements required on the positive and negative side. Now when it comes to the nominal shear value, you are supposed to give you the value of u is 240. Okay, the value of u is 240. So therefore correspondingly the nominal stress value that you are going to get will be 1.45. okay, you can reduce the value as 1.45. so now I need the value of AST, that is you can see that I am going to do from that so small AST, that is area of the one steel, 3.144. what is C21? So C21, if you see C21, that is the diameter of the reinforcement positive they have taken. Okay, so therefore if you see that the AST provided that you are going to see, and this is what the actual percentage of steel that you are going to provide. You can see that the actual percentage of steel. Okay, still if you want to have a doubt, you can make a clear actual percentage of steel, that is C4 and C6 will be your breadth and depth. Okay, yes. So you can see that the nominal shear you got, the AST is nothing but the area of the one reinforcement. Okay, yes, correct. So and you can see that the AST that is going to provide is this much. Okay, you can see that how it is AST into C36, which is 36, so that is C36 into, and the next is C30, which is C30. C30 is the number of reinforcement that you are actually provided. Okay, therefore the percentage of steel that you are going to provide becomes this much value. Okay, that is 0.73, and now you are supposed to find out the percentage of permissible shear stress. This permissible shear stress you are going to get from the table 19. Okay, going to get from the table 19. I will tell you. I will tell you the table 19. Yeah, so this is table 19. You know, it will be the percentage of tensile reinforcement that you are going to provide. Okay, percentage of tensile reinforcement that you are going to provide, and we are going to provide M25 grade of concrete. And what was the value of this permissible shear stress value, which is going to depend on percentage of steel and the grade. It is 0.73. Okay, it is 0.73. You can see that 0.73, I can go to 0.75, and in the 0.75 with M25 grade you are getting 0.57. Okay, so 0.57 I can get the permissible shear stress as per the table is 0.57. Okay, and what about the maximum shear stress? The maximum shear stress you are going to get at the bottom only with the table based on the grade of concrete. For M25 the maximum shear stress is 3.1, right? So this is 0.57, this is 3.1, and now when you calculate, your nominal shear stress value should be less than the permissible shear stress, that is 0.57. If it is less than, then provide minimum shear reinforcement. If your nominal shear stress is more than this permissible, it is 0.57, then design it, and that value should not be more than 3.1. Now let us check the shear strength of the concrete VUC they have given. it is permissible shear stress into breadth and depth of the beam into 1000. Okay, that will give you, this is the permissible, that is the shear strength of the concrete. The shear to be carried by the steel is given by VUS, that is nothing but this minus this, and the diameter of the reinforcement for the stirrup that I am going to use 10 mm, and the area of the one stirrup, it is already calculated, and therefore directly you can see that the spacing of the stirrups is this one. Now where we have checked this, you can see your nominal shear stress value to you, it is 1.45, whereas your permissible shear stress value, okay, is permissible shear stress is 0.57. That means your nominal shear stress is more than the permissible shear stress, therefore you are supposed to design the shear reinforcement. Whereas your nominal shear stress value, that is 1.45, is not greater than the maximum shear stress value 3.1, it is less, so therefore it is safe from the shear. Therefore you can see that it is the actual spacing, okay, so the spacing of the stirrups that what to get calculate, so it should not be greater than 300 mm, or it should not be, therefore I can give a final spacing of 200 mm center to center. Okay, so this is how you are supposed to do the design, right? So according to that, now we have done the first design of this set of beam. Okay, yes. Now let us go to the second set, that is beam 17 and 19. You can check beam 17 is this one, it is 9 inch into 1 feet 8 inch, and 19, that is also same, 17 and 19. So therefore I can go 17 and 19. So let us go to 17 and 19. Okay, yes. Now this will be, the grade of concrete will be 25, whereas this will be 415, and you know the breadth will be same 300, effective cover will be 20, this will be 550. Okay, so definitely this has to be 570. And now the design shear force according to this, you can see it is 268, I can make it as 270. Okay, still it is much more higher, 270. Okay, then the positive bending moment value according to this, you can see the positive bending moment is 190, I can give 190, whereas your negative bending moment value, it is 391, I can give it as 392. Okay, it is 392. Therefore you are supposed to calculate mu by bd square value is 2.0, almost I can take it as 2, and another is 4.3, still much more higher value. Okay, so therefore if you see that the percentage of steel that for 2.0 what you are going to get, you can see mu by bd square, it is almost 2. Okay, almost 2, 2.0, almost 2 with 415. 0.618 is the percentage of steel, 0.618 is the percentage of steel, and you know this value, it is you are getting value 1.2, and you know as per IS 456 2000, the maximum percentage of steel that you can provide for a beam cannot be more than 4%. Therefore since that value is not available, I can take the percentage of steel as around 1.5%. Okay, let us check whether it is going to fail in the shear or not. So now definitely you are supposed to provide this value, so it will be calculated based on the percentage of steel, and the same thing I am going to maintain 16 and 20 mm. Therefore I am going to calculate the individual areas. Okay, and definitely I am supposed to calculate now number of reinforcement. So you can see that it is anyhow 6, and now this becomes 8, means 9, I can give 10 numbers. Okay, and now the nominal shear force value, you know it is 270. Okay, it is 270, right? So now you want the nominal shear stress to be calculated. It is 1.64, and you know this is AST, and this is corresponding that the one that you are going to provide. And you can see this is the percentage of steel, 0.73, same value. So from the table I can get this as 0.57 itself, no changes. So, and this also it will not change since the grade is same, that is 3.1. okay, so it is not going to change, 3.1. and you know anyhow this the same procedure. Now VUC value I am supposed to find out. This is my VUC, and VUS value will change, it is 170. So this also I am going to maintain 10 mm diameter only. So therefore when I calculate the one individual area, and now this is the spacing, now the nominal shear stress value is 1.64 nominal shear stress, whereas permissible is 0.57. okay, so nominal shear stress is more than permissible, therefore you are supposed to design the value. okay, and whereas this is less than 3.1 safe, therefore I can provide the stirrups of spacing at 180 mm center to center, right? Yes, so like this I can design the beam. So the another set of beam is ready. So like this, let us do all other beams in the next video. okay, thank you learners.